Welcome all. Today we are starting with the numericals of Chapter 19 Thermodynamics, and we'll be dealing with the numericals of heat and work. The first numerical that we are considering today is question number 6. In this, a bullet of mass 20 gram strikes a target with a velocity of 100 meters per second and comes to rest. So the final velocity is 0. 50% of the kinetic energy is used to increase the temperature by 25 degrees. You have to calculate the increase in the internal energy of the bullet due to rise in temperature and the specific heat of the material of the bullet. Now, the kinetic energy is half mv square initial and the final is 0. So the change in energy that takes place is 100 joules. 50% of this energy is used to increase the temperature. Now we know that the kinetic energy causes a change in temperature which increases or changes the internal energy of the bullet. So the internal energy of the bullet will be 50% of kinetic energy, which is 100, and it comes out as 50 joules. And this is causing a change in temperature. So 50 joules will be equal to mc delta T. The change in temperature is 25 degrees Celsius. Substituting the values, we get the value of specific heat capacity as 100 joules per kg per degree Celsius, which can be converted into calories if you want. Question number 10. A 5 kg hammer falls with a velocity of 1 meter per second on the piece of lead of mass 300 grams at 27 degrees Celsius. We have to calculate the number of strokes that are required for melting the lead. Now the kinetic energy of the hammer is half mv square, which is half into the mass of the hammer and its velocity. That comes out as 2.5 joules. Now heat energy for melting the lead is mc delta T and ml. The melting point of lead is 327. So first the temperature falls down from 27 to 300. It rises from 27 to 327 and then it melts. So the change in temperature is 300 degrees. So when the change in temperature is there, heat energy required is mc delta T. The specific heat capacity of lead is 125 joules per kg per degree Celsius, and the latent heat of lead is given as 6 kilocalories, which is 6000 into 4.2 joules. So converting this and adding both the energies, we get it as 18810 joules or 18,810 joules. Dividing this energy by the kinetic energy of the hammer, we get the number of strokes as 7,524. Numerical 12. Water falls from a height of 20 meters at a rate of 100 kgs per second. We have to calculate the heat in calories per second on striking the earth. We are assuming here that the whole of heat gets converted into energy. Now the water is falling, the energy that it possesses per unit time is mgh upon the time. So the heat produced per second is mgh upon the time, which is 1 second. So substituting the values, the mass per second is given. The rate of falling per second is 100 into 9.8 multiplied by 20, which is 19,600 joules. Dividing it by 4.2 or 4.18, we can get our answer as 4.67 kilocalories. Question number 13. From what height should a piece of ice fall upon the ground so that it completely melts? We are assuming that all the heat produced remains in ice. So by conservation of energy, ice is melting. The heat required for melting of ice is ml, where L is the latent heat of fusion. and it's falling from a height, so it possesses potential energy. Equating the two, we get the value of height as L upon G. That comes out as 34.28 into 10 to the power 3 meters. That is 34.28 kilometers. 16th, what amount of work will have to be done in converting 1 kg of water into steam at 100 degrees Celsius and normal atmospheric pressure? The volume of 1 kg of water at 100 is 10 to the power minus 3, and that of steam is 1.671 meter cube. The normal pressure is the atmospheric pressure, that's 10 to the power 5 Newton per meter square. Now we know that the work done is equal to P delta V. So substituting the values of pressure as 10 to the power 5 and the difference in value as 1.671 minus 10 to the power minus 3, we get the answer as 1.670 into 10 to the power 5 joules. The next question that we've considered is solved example 8 of your textbook. From what height should a piece of ice fall so that it melts completely? Only 1/4 of the heat is absorbed by ice. Now, when the ice is falling, the energy it possesses is potential energy, mgh. 1/4 of the heat is absorbed, so the heat energy absorbed by ice for melting is 1/4 of mgh, which will be equal to ml. So h is equal to 4l upon g. Substituting the values, we get the height as 13.6 into 10 to the power 4 meters.